Highlighting this report period on November 16th was the successful launching from Complex 34 at Cape Canaveral of the third Saturn C-1 flight vehicle, SA-3. Similar in major aspects to the previously successful SA-1 and SA-2 flights, SA-3 performed several additional missions contributing to development of the Block II SA-5 and beyond version of the vehicle. For example, an engineering model of the ST-124 stabilized platform was carried as a functional passenger, though not in control. And although no stage separation was attempted, Block II retro rockets were successfully test-fired. The booster carried a full load of propellant, some 750,000 pounds, instead of the 620,000 pounds carried earlier. SA-3's weight was almost as great as that of later vehicles, which will have 188,000-pound thrust engines, although SA-3's 8 H-1 engines were rated at 165,000 pounds thrust each. SA-3 was the most heavily instrumented rocket ever launched by the United States, transmitting 716 measurements to ground stations. Analysis of telemetry data indicated that the vehicle performed precisely as expected. SA-3 reached maximum altitude of 104 miles, range was 270 miles, and velocity 4,000 miles per hour. Flight time to impact was slightly over 8 minutes. SA-3's two inert upper stages, laden with 95 tons of water simulating fuel, were deliberately exploded on schedule at 104 miles altitude, 292 seconds after liftoff, in a study of the basic physics of the ionosphere. Satisfactory data on this experiment, known as Project Highwater, were recorded. A similar experiment had been conducted on the SA-2 flight. More damage was done to ground support equipment by SA-3 than on previous launches because of lower liftoff acceleration resulting from the additional 160,000 pounds of propellant. However, damage was not considered excessive. Half a mile north of SA-3's launch site, construction progress is on schedule at Launch Complex 37, being built to handle launching of Block II vehicles. Pad B is expected to be operational in March. Beneficial occupancy and final inspection of the Launch Control Center was accomplished in early November. Work on the launch site surface structure is progressing, with hydraulic lines being installed and work on pneumatic lines underway. Pad A is scheduled to be operational about 3 months after Pad B. Erection of primary structural steel for the umbilical tower is complete, and delivery of structural steel for the launch pedestal has begun. At the automatic ground control station, concrete is being finished and drains and electrical conduit installed. The new combination support and hold-down arms for Block II launch pedestals were delivered by the manufacturer, Hayes International of Birmingham, to the Marshall Space Flight Center this quarter for testing. Afterwards, they'll be shipped to the Cape for installation at Launch Complex 37. The arms will support and hold down the Saturn vehicle after ignition until proper thrust condition for liftoff. The fourth Saturn flight vehicle, SA-4, was removed from Marshall's static test stand on October 1st, having completed its static testing with a full duration firing the previous week. After undergoing post-static rework and modification, the SA-4 booster was transferred to final checkout on October 22nd. A micrometeorite detector device designed to measure the density of small, high-speed particles encountered at high altitudes will be initially flown aboard SA-4 as an inactive passenger to see how it withstands environmental conditions. If telemetered results are satisfactory, the device may be operative on later Saturn flights. Three static firings of the test booster SA-T4.5 were held during this report period, with engines developing 1.5 million pounds thrust. Test objectives were to check integrity of the propulsion system and effect of the 188K engines on the flame deflector. The test booster was removed from the stand on November 15th. The final engine was installed on the booster for the fifth Saturn flight vehicle, SA-5, on October 11th, and the stage was later released for pre-static checkout, expected to be completed in mid-January. A decision has been made to fly a Jupiter-type payload body on SA-5 rather than the Apollo boilerplate configuration as originally proposed. Assembly of the booster for the sixth Saturn flight vehicle, SA-6, begun on September 24th, proceeded this quarter with clustering of tanks completed and installation of engines underway. Fabrication of the tail section of the booster for the seventh flight vehicle, SA-7, was finished in December. The vehicle's interstage adapter was also completed. SA-7 booster assembly is scheduled to begin in January. Modification of Marshall's dynamic test stand to accept the dynamic test vehicle SA-D5 was finished in October. Major alterations included cutting away of a portion of the grillage in order to accommodate the longer Block II type vehicle, plus installation of new support pedestals at the base of the stand. Assembly of the Block II dynamic test booster was completed early this quarter, and the stage was erected in the dynamic test tower on November 13th after weighing and center of gravity determination. The S-4 hydrostatic dynamic stage, which forms the upper stage of the SA-D5 dynamic test vehicle, was completed this quarter by Douglas Aircraft Company, S-4 prime contractor at Santa Monica, and was prepared for shipment. On October 26th, the stage was moved from the Douglas plant to the docks at nearby San Pedro. Cradled in a specially built 25-ton transporter, the S-4 was loaded aboard a steamship to begin its 3,500-mile journey to the Marshall Space Flight Center. This marked the first time a Saturn stage has been shipped by water from a West Coast manufacturing site through the Panama Canal to a test or launch site in the east. Other stages will follow. The S-4 stage arrived at Marshall on November 16th after a 23-day journey. It had been transferred to the Saturn barge Promise at New Orleans for the river portion of the trip. At Marshall, the S-4 stage was installed atop the SA-D5 booster. The stage is scheduled to remain at Marshall for several months. Its external configuration, weight, and other characteristics are the same as those of the flight stage, which will be a part of SA-5. After installation of the instrument unit, payload adapter, and payload to complete the vehicle, SA-D5 was made ready for dynamic testing, scheduled to begin in January. Modification of Marshall's C-1 static test stand to accommodate two boosters continued this quarter. Steel superstructure and basic plumbing now stands at the 4th level. Adjacent to the stand is the annex, which will house office and shop personnel. Units such as the elevator, air conditioners, and heating ducts are being installed. Using a scale model of the Saturn booster tank assembly, a series of liquid oxygen boil-off tests were run at Marshall to determine system flow under simulated flight conditions. For safety, liquid nitrogen was used to simulate locks. Purpose of the test is to find out how much boil-off occurs in a given time and to verify that tanks empty simultaneously. Discharge tubes carry the liquid nitrogen from the test stand to the point of discharge. Liquid nitrogen vapors hold close to the ground and are highly toxic. Line flow is monitored by movie cameras to study vortexing conditions in the suction line and undesirable gassing in the system. Using scale model tanks to represent Saturn boosters, tests are being run at Marshall to determine the most desirable method of controlling propellant dispersion in event of range safety destruct or accidental explosion. An external destruct system has proven most effective using primacord and flexible linear-shaped charges installed longitudinally on the cylindrical portions of all tanks. Upon ignition, these charges rupture the containers, and internal tank pressure causes an outward dispersion of the LOX and RP1 propellants, greatly reducing their mixture and the resulting explosion. After engineering refinement, the external destruct system will be employed on SA-5 and subsequent vehicles. The first two production models of the ST-124 stabilized platform were delivered to Marshall this quarter by the manufacturer, Bendix Corporation. ST-124 units will be flown as functional passengers, though not in command, aboard SA-5 and SA-6. Beginning with SA-7, the ST-124 will be the command unit. One of the ST-124s was later shipped to Holloman Air Force Base, New Mexico, for a series of rocket sled tests. 4 telemetry links provide 48 channels of information to measure performance during the 7-second, 5-mile trip along the sled track, where the unit sustains a maximum of 8 Gs for 3 seconds. The sled reaches maximum speed of approximately 1,000 miles per hour. Test results were satisfactory, indicating the ST-124 will stabilize as desired. A prototype of the Saturn Block II instrument unit, which will house the ST-124 stabilized platform, together with other components necessary to perform the functions of guidance, navigation, instrumentation, measurement, and telemetry, began undergoing checkout this quarter in a recently completed automatic checkout facility at the Marshall Center's Astronautics Division. The facility, which will also simulate Saturn C-1 vehicle checkout at the launch site, consists of a launch control computer, signal conditioning, countdown clock, digital data acquisition ground station, automatic instrumentation stimulus, instrument unit electrical support equipment, manual electrical support equipment, S1 stage substitute, power distribution, systems interface, facility recorders, propellant tank system, and instrumentation unit interface. The automatic checkout facility has the prime objective of assuring compatibility of the entire Saturn vehicle with each unit of its electrical support equipment and confirming design of such equipment prior to its installation at Cape Canaveral. The vehicle is simulated for checkout purposes by utilizing flight-type distributors, sequencers, and other electrical flight hardware. At Marshall's Quality Assurance Division, an automated checkout concept for Saturn stages was used in part for the first time this quarter in connection with the SA-4 booster and will be used in its entirety next quarter on the SA-5 booster. The checkout concept includes 10 widely separated remote stations, each assigned specific test missions, serving as satellites to the central computer complex, the heart of the entire system. The computer complex consists of 3 Packard Bell 250 general-purpose computers, communicating with each other by sharing common memory elements under a master-slave structure. The Saturn hardware forms a closed-loop system which provides stimuli generation, switching, and response retrieval, all under computer control, Transmissions between the computer and test stations are digital, permitting location of the test stations at a considerable distance from the computer complex. The test stations include instrumentation and telemetry systems and components, guidance and control systems, radio frequency systems, network systems, electrical components, and mechanical systems, assemblies, and components. At Marshall's Michoud operations in New Orleans, being readied for Chrysler's production of C1, C1B boosters, renovation and construction work this quarter included build-up of the shipping and receiving ramps from which the huge plant is serviced by rail and truck. A new 40-foot vertical lift door is also being installed at one end of the building to permit movement of boosters. All construction work is being done under direction of Michoud's support services contractor, the Mason Rust Company. Installation of Saturn booster assembly fixtures at Michoud by Chrysler was well underway this quarter. Early in November, the barrel assembly fixture was emplaced in the tail assembly area. Here, the booster's upper and lower thrust rings, skin assembly, and shear web assembly will be constructed. The thrust structure fixture was also installed on its foundation. Optical alignment to precisely level the large fixture was accomplished by the vendor and checked by Chrysler Tool Engineering personnel. This fixture will be used to tie together the barrel assembly, the 8 outriggers, and their connecting structure. Installation of rails, control cabs, hoists, and electrical circuits for the overhead crane systems in the tail assembly area continued. These cranes will be used to move the upper and lower thrust rings, barrel assembly, thrust structure, and other components from one workstation to another in the tail assembly area. Work on the surface treating pit is progressing, with laying of forms and pouring of concrete accomplished. The sump pump area and flooring and sidewalls for the area to contain the large treating tanks have also been finished. At Douglas Aircraft Company's Sacramento test facility, a highlight of this report period occurred on October 4th. The first successful full-duration static firing of the 6-engine S-4 stage battleship configuration. All RL-10 engines ignited properly under simulated altitude conditions and fired for 7 minutes at full thrust of 90,000 pounds. The bottom sections of all diffusers on test stand number 2 exhibited extreme erosion and required replacement with diffuser caps taken from test stand number 1. Certain modifications were made to allow greater cooling of these caps by increased water flow through them. The S-4 all-systems vehicle, after tank cleaning in Douglas's hydrostatic tower, has been moved into a plant area where installation of its electrical systems will take place, and the stage made ready for its static firings at Sacramento in 1963. In the vehicle checkout area, the first set of ground support equipment has been installed. This is the Phase 1 set of GSE, which had previously been systems tested in Douglas's Culver City Facility System Integration Area. All available articles of Phase 2 GSE have now been installed in the systems integration area, and GSE system tests have begun with the GSE test set and the S-4 stage mock-up. A telemetry test and evaluation console is used to monitor the various instrumentation circuits. During these operations, checkout and calibration procedures are also developed. In an adjacent testing bay, vehicle and GSE end items and subsystems which require individual checking are acceptance tested against specialized consoles. Phase 2 equipment will be shipped to Sacramento for use on the all-systems vehicle in January. Other sets will later be checked out for delivery to the Saturn launch site at Cape Canaveral. Douglas has also begun studies on application of the S-4B stage, third stage of the advanced or C5 Saturn, to the C1B vehicle. The work includes investigation of minimum changes to the C5 type stage for C1B missions, plus S1, S4B interface and stage separation. The S4B structural layout drawings being prepared by Douglas are nearing completion, and work has begun on detailed stage structural drawings. Plans for a facility for ground testing of S4B stage at Douglas Aircraft's Sacramento area were outlined in late November. The test complex will include static test stands, blockhouse, propellant, and high-pressure gas systems and supporting utilities. At Rocketdyne Division of North American Aviation, contractor for the J2 engine, which will power the S4B stage, a major milestone was reached this quarter when, on October 4th, the first full-duration static test of the liquid hydrogen-fueled engine was held. Coming 8 months and 5 days from the time of the J2's initial static test, the firing ran for more than 4 minutes at full thrust of 200,000 pounds.